Okay, so continuing on from where we left off in the last lecture, we started into vectorization. That's the last unit in the course. And what I wanted to mention just briefly is that if you're using Linux systems, which is the case for the lab that we're using for the course, if you want to find out information about the processor that you're using, like on the particular system, you can dump out the contents of proc CPU info. When you print this out, it will give you like all kinds of information, more than probably you really want to know about the CPU you're using. But in particular, the sort of thing that you can look for if you're on like an Intel x86 or either 32 or 64-bit system, there's flags that indicate particular features, which are some of the SIMD extensions, like vectorization, vector processing extensions like MMX, SSE, and all these things. So you can find out like what specifically is supported by the particular processor that you're using on the system that you're on. Or if on ARM systems, you can look for Neon. This is the name of the vector processing kind of instruction set extensions for ARM systems. So vectorization, I want to look at vectorization in a little bit more detail. So at the top of the slide, I have a code example, which is computing essentially like a linear function. It's computing AX plus Y. And you're essentially giving it a vector of X values, like an array of X values, and then you're just computing AX plus Y, where A is a constant, Y is a constant effectively that's passed in, and X is, you know, some vector. And you're just computing this in a very straightforward way in terms of a loop. So we can apply a vectorization to a loop here. Essentially what we have is many different operations which have the same structure, because the body of the loop here is repeated over and over again for each iteration of the loop. So for each iteration of the loop, you're essentially performing a very similarly structured computation. So this is something that could potentially lend itself quite well to vectorization. Anyway, when we're vectorizing, basically making sort of vector versions of code for loops, this is referred to as loop vectorization. Another sort of situation where we could apply vectorization is sometimes what's referred to as basic block vectorization. We don't necessarily have a loop involved, but we have some kind of similar computational structure. So we have like 4 different lines of code here, and although they're all using different variables, they have the same structure. Like we're basically multiplying 2 values together, adding it to another value, and then assigning the result to another value. So you could imagine, for example, maybe vectorizing the code in the following way. You could load like D, H, L, and P all into one vector register. You could load C, G, K, and O all into another vector register. And then you could load B, F, J, and N into another vector register. And then what you do is a vector multiply to do this multiplication, and then a vector add to add that result to the vector that's holding the first term of this sum. And then we could use a vector write, like a vector store operation, to store the result out to memory wherever these variables are sitting. So there's basically the sort of pattern you see with vectorization is there's some kind of common structure. You're doing like a similar computation to multiple pieces of data, and then the idea is you can combine these things together into vector operations. Any questions? So in terms of how we can think about loop vectorization, I find that a good way to kind of understand what's going on is to think in terms of loop unrolling. This is a type of optimization that compilers often perform. So if you've taken a course on compilers, perhaps you might have seen that term before. But the idea is very simple. I mean, essentially we have a loop, for example, like what's shown here. We're doing some computation involving 3 arrays, A, B, and C. And I'm going to assume, just to make the example simpler, suppose that the number of times that we're iterating n is a multiple of 4. So and we're assuming n is evenly divisible by 4, just to keep some other complications from creeping into this example. What we can do is we can apply what's called loop unrolling. And essentially what this does is, I mean, if you have a loop, if you know how many times you're iterating, you can just write it out without a loop by repeating the same line many times. And essentially this is what loop unrolling does. It just takes the loop and rewrites it as if it wasn't a loop by just repeating similar instructions. But we're not going to fully unroll the loop like n times. We're just going to unroll it kind of 4 times. So what we'll do is we'll take kind of 4 iterations of the loop and put them all into the body of the iteration of this new loop. And you'll notice now when we're looping, instead of incrementing I by 1 each time through the loop, basically each increment of I corresponds to like 1 more iteration of the loop. Here, since we're effectively doing 4 iterations of the original loop per 1 iteration of this new loop, we're going to increment I by 4. And essentially what these 4 lines correspond to here are the 4 iterations of the original loop that have been merged together into a single iteration of this new loop. So this is what I mean by loop unrolling. And once you unroll a loop in this way, it kind of becomes very easy to think about vectorization, because essentially what I'm doing is a very similar kind of computation 4 different times. I'm basically taking and adding 2 values together, and then storing the result into some other place, like assigning the result to some other place. So what I could do is I could, for example, load all 4 of these b values, b of I plus 0, I plus 1, I plus 2, I plus 3. I can load these all into a vector register with a vector length of 4, for example. I could load all these a values here, a of I plus 0, I plus 1, I plus 2, I plus 3. I can load them all into another vector register, and then I can do a vector add to add these 2 sets of values together. And then I can do like a vector store to write the values into this other array here. So kind of in terms of what we're doing here, essentially we're basically loading all the elements in A from I to I plus 3 into one vector register, which I just called V0 for illustrative purposes. Then we load the elements BI to BI plus 3 into another vector register. We add these 2 vector registers using a vector operation and write the result into another vector register. And then we can do a vector store of that register into CI through CI plus 3. So again, when we have this kind of repeated structure, which you fundamentally always have with loops, loops are basically repeating the same thing over and over again, it tends to lend itself fairly well to vectorization. And the syntax that I'm showing at the bottom of the slide, sometimes people like to use syntax kind of like this. It's not, no C++ compiler compiles it per se, but it's a helpful way to kind of express the idea of things being vectorized. So this is trying to express the idea that we're taking this, array A, and we're accessing like 4 different elements from I plus 0 up to I plus 3, and grabbing all of them at once. And then same thing for the vector B, we're grabbing like 4 elements at once, and then this is basically kind of representing a vector addition operation. And then we're taking the whole thing and assigning it to this vector C. Anyway, this is not a standard syntax, but sometimes it's a useful way to write things just to express the idea that you're using vector operations. And I guess it's kind of a little bit like MATLAB, syntax in MATLAB, except MATLAB uses round brackets rather than square brackets, I guess. Any questions about this example or this slide? So in terms of how we approach vectorization, I guess there was a question at the end of the last lecture which kind of touched on this, but I'm going to go into a little bit more detail. Like, how do we actually cause vectorization to happen was essentially I guess, more or less paraphrasing a question from the end of the last lecture. So there's a number of ways that vectorization can take place, and I've listed on this slide sort of from the most simple approach, where you don't really need to do anything special, down to like the really horribly painful way to do things. And as we go from the top to the bottom, although things are easier, the higher up things on the slide are easier to do. But as we proceed down into the more difficult things, we get more and more control. So it's a trade-off between like how simple do you want it to be to achieve vectorization versus how much control do you want over the vectorization that takes place. And in some cases, you might want to exert some control, because maybe if you don't exert any control, the compiler just says, well, I'm not going to vectorize, or I don't think I can vectorize. It's not clear to me that this is a safe transformation to apply. Anyway, so the most simple approach is just auto-vectorization. Most compilers will just automatically do vectorization for you as part of the optimization process, at least provided that you have that functionality enabled in the compiler. So like GCC and Clang both have auto-vectorization, for example. Well, any compiler these days, reasonable compiler, is going to have auto-vectorization support. So basically, you don't do anything. You just compile your code, possibly specifying some option to say, make sure this optimization of vectorization is turned on. And the compiler will look at your code, and if there's places where it sees that it looks like it's going to benefit you from doing vectorization, and it's clear that it's safe to transform the code in that way, it will just go and apply the transformation for you. Then we can move from this to auto-vectorization with compiler hints. In this case, what we do is we add extra annotations to our source code to give hints to the compiler about whether it's safe, things that it might not know about the code. Like, the problem with auto-vectorization is that in a lot of cases, the compiler won't be able to vectorize the code, either because it can't tell that it's safe. Because like when a compiler is optimizing your code, it's pretty much free to do anything it wants to, as long as it doesn't change the observable behavior of the code. In other words, if the transform code with the optimization runs as if it was the original code, it has the same observable behavior, then the compiler is free to do anything it likes. But the problem is, for a lot of optimizations that involve vectorization, the compiler cannot tell that it's safe. It cannot tell that by applying vectorization to your code, that it's not going to change the computation that you're actually performing. Because essentially what vectorization does is it reorders computation. Because when you take several iterations of an unvectorized loop and merge them together, when the things are running as a single sequential loop, each iteration happens one after the other. They don't happen at the same time. Like, one happens, then the next iteration happens, the next one. If you merge a bunch of iterations together by vectorizing, what you're causing to happen is things that used to happen one after the other now happen in parallel. And because you're changing the order that things happen in, if there's the wrong type of data dependencies between some of the data that you're operating on, you could actually end up computing a different result. In other words, you take the code from something that's perfectly fine and working and make it into something that doesn't do what you wanted anymore. So this is essentially one of the major problems with auto-vectorization is often the compiler, it can't determine that things are safe, or the other problem is not that it can't determine that it's safe, but rather the compiler is not going to apply an optimization to your code that would slow it down. And if certain, it's not always true that vectorization will make your code faster. In certain circumstances, it could make it slower. And the compiler has to make its best judgment in terms of looking at the code you wrote and saying, well, is it likely that there would be a benefit to doing the vectorization? And sometimes either it won't have enough information to determine the transformation is safe at all. Like it can't even tell whether it will break your code by vectorizing it. In other cases, maybe it knows it's safe, but it can't tell enough information to know whether it's a profitable thing to do. In other words, is it actually going to make the code faster, or will it slow it down? And of course, in those cases, even if it knows it's safe, but it might slow your code down, it's not going to apply the optimization in that case. So these are the problems that kind of surround auto-vectorization. So the first level of a little bit more difficulty, but it's not too overbearing on us, is we can provide hints to the compiler, things that allow it to make better judgments about, is it safe to apply vectorization in this case, or is it something that's likely to be profitable, by giving the compiler more information to base its decision on. We can take things to another level where we have some kind of explicit directives introduced into the language which allow us to take some control over vectorization. And there's various different libraries that allow us to do this. There's things like OpenMP, for example, is a very popular one. If you had a course in concurrency, parallelism, and so on, there's maybe a good chance you might have used OpenMP. And basically, the only things we're really going to talk about in the course are like items 1 through 3, mainly with an emphasis on number 2 here. We'll talk a little bit about OpenMP at the end. But we can take things to even more levels of complexity where we start using some kind of built-in vector types in the compiler. Like often, most compilers will provide some kind of built-in types that you can use that give access to the vector types on whatever architecture you're working on. Or maybe using compiler intrinsics, which are basically built-in functions in the compiler, which effectively give you kind of very low-level access to vector instructions in the CPU architecture. Maybe there's like sometimes might be a one-to-one mapping between some intrinsic functions, like functions that are built into the compiler, and actual CPU instructions, vector instructions. So you want to use a particular vector instruction, there's a particular function that you call to access it. Or we can take things to another level and we can just say, well, forget the compiler, we're just going to write our own assembly code. And then we can use whatever vector instructions we want, because basically we get to choose the instructions that are being executed. But as we proceed from the top to the bottom of this slide, like going from item number 1 to item number 6, things get progressively more and more difficult to do, more and more error prone. The other thing too is like kind of once we go past item number 3, like items 4, 5, 6, they become extremely platform dependent, because you're starting to use like functions or data types or actual assembly instructions, which are going to depend highly on the particular processor architecture you're building for. So if you write highly optimized vectorized code for x86 using maybe assembly language or using some of these intrinsics, and then you go, oh, but now we need to build our product for ARM. Well, now you get to rewrite all that code, because all of it's useless to you, because it's all depending on the fact that you're using x86, for example. Or maybe it's depending on, even within a particular processor family, there can be differences, because there's many different versions of like vectorized extensions to x86. There's like SSE, well, there's MMX, which came first, and I think, and then SSE, and there's various different versions of it, and then there's AVX, and depending on which particular type of Intel x86 processor you have, maybe you have certain instructions, maybe you don't, and then like it just opens up all these problems. So it's maybe better to not go with items 4, 5, 6 here. Just stick with letting the compiler kind of do the heavy lifting in terms of generating assembly, and you just tell the compiler when you're building, well, this is for this particular processor type, and then it will know which particular vector instructions are available, and it can just use them. Anyway, so again, we're going to focus primarily on kind of auto-vectorization with compiler hints in this course, because it's kind of a very, very portable approach. So, and you can often get fairly good performance by doing so. Any questions about any of that? So starting with auto-vectorization, I guess I've already covered some of these things with the comments that I made to begin with. So, I mean, again, auto-vectorization is essentially letting the compiler do the work for you. You don't do anything special except enable vectorization, maybe with some compiler option, and the compiler will do it in cases where it knows it's safe and it's likely to be profitable to do so. In other words, it will improve the performance. The problem is that another advantage is it's less error prone. Effectively, the compiler is doing these transformations to your code for you. So as long as you have a stable compiler that doesn't have bugs, which is probably the case for most people who are doing development, if you're using a decent compiler, if not, get another compiler, if the compiler doesn't have bugs, then you're guaranteed that there's not going to be any problems with these transformations for vectorization. But the main problem is the one that I was kind of emphasizing with the previous slide, which is that often it's difficult for the compiler to make a judgment as to whether the transformation is safe to apply or whether it's profitable. Maybe it knows it's safe, but is it actually going to help? In which case, probably to be conservative, the compiler is not going to go out of its way to do something that might make your code slower. So if it's not sure, it'll probably just back off and not do it. And the problem is a lot of the time, the compiler won't be able to vectorize your code. And a lot of the time, it'll be cases where when you look at it after the fact, if you find out that the compiler is not vectorizing, you say, well, why? Is the compiler like stupid or something? Like, it's obvious to me this should be vectorizable. But the problem is when you look at it in more detail and say, well, maybe aliasing can happen and other things can take place. Like, how is the data aligned? Does the compiler know that the data is going to be aligned with whatever alignment which is required to load? Like, when you're loading data into a vector register, it might need stricter alignment than if you were just loading an individual element somewhere from memory. So due to other things, like maybe the compiler can't tell how the data is going to be aligned at compile time, or it can't tell other things like whether different pointers in your code can alias to one another. So it can't tell whether two values it's reading are actually the same value or not. These things can prevent the compiler from being able to vectorize. And these are the kinds of things that maybe it might not strike you at first, but the compiler, when you realize the compiler is not vectorizing and that after the fact, you understand why, then you go, oh yes, this makes sense. The compiler could break my code if it did this. So there's a lot of circumstances where the compiler might not vectorize, but you might expect that it would. So in GCC, there's both a loop vectorizer and a basic block vectorizer. I mean, basically GCC and Clang both provide vectorization support, and probably any reasonable compiler these days is going to, including Microsoft Visual C++ compiler. If you're using GCC though, if you use the -O option, -O to specify the level of optimization, you have to use a level of at least 3, otherwise it won't turn on vectorization by default. There are individual compiler options that you can add to turn on vectorization, even if you're not using level 3 of optimization. But if you're just kind of going with the basic route of just using the -O option, you should use at least level 3. GCC fully supports OpenMP, which again, this is like basically a library and also some additional language support that adds some functionality which is useful for both vectorization and also more generally for concurrency as well. Anyway, so it has OpenMP support as of GCC 6.1, which is pretty old. We're up to 9 now. In terms of some options for the compiler that relate to vectorization, a key one is this one, F3 vectorize. So this option will turn on vectorization. So if you're not using like O3, like at least optimization level 3, but you still want to turn on vectorization, you can do this by using this particular option here. Also, there's a couple of other options which are helpful for giving you some information with respect to vectorization, because like I said, you may turn on vectorization and just assume that the compiler vectorizes your code, but it will only do this if it deems that it's safe and also it's profitable. And the thing is, you may think it's safe and profitable, but you may be wrong, and the compiler may decide not to vectorize things. So these two compiler options here are for giving you kind of more information. This option here turns on additional informational messages that are printed when you're compiling that identify places in the code where vectorization was successfully applied. So you can go, oh, yeah, it did vectorize here, because the message is being printed out saying that maybe this particular loop or something was vectorized. Also, there's an option where you can tell the compiler to tell you places where vectorization couldn't be applied. And maybe this also might be quite a bit of interest to you as well. Again, because sometimes the compiler might not vectorize in places where you think that it should be able to, but there's some special case that the compiler knows about, but you've overlooked, which make it either not safe or not profitable necessarily for the compiler to optimize. Then there's an option in GCC called FOpenMP SIMD. What this does is it enables some of the OpenMP support, namely the OpenMP support for SIMD. So there's actually vectorization support in OpenMP, which requires some extra language extensions and so on. So this enables them. Again, OpenMP is quite a popular library. The next two options are not really directly for vectorization, but they can be quite useful when you're really interested in optimized code and so on, and kind of wondering, like, when the compiler vectorizes the code, what did it really generate for the code that was produced? Because it may say that it vectorized the code if you enable the messages to say, please let me know when things were vectorized. It may say it was vectorized, but yeah, what code was generated? Because some vectorized code might be better than others. So you might actually want to look at it. So any C++ compiler I've ever seen, it has some kind of option where you can say, don't actually produce object code, but instead just generate the assembly code that you would actually assemble to produce the object code. So with GCC and Clang, they have a -S option, which will cause the compiler not to produce object code as output, but instead it will just generate the assembly code that would be assembled into the object code. So you can actually look at the assembly instructions that are being generated by the compiler. And this can be very, very useful when if you're really interested in fine-tuning and kind of squeezing the last bit of performance out of things, but you don't necessarily want to write the assembly code yourself. Often what you'll find yourself doing is you kind of add a bunch of hints, annotate your code with a bunch of hints to the compiler to try to do the best job possible, and then you look at the assembly code that's produced and you go, well, did it give me something that's kind of reasonable for what I want? So this is a very common option to want to use. Also, in conjunction with this option, there's another one called -F verbose ASM, and what this does is it says when the compiler is generating the assembly output, it should add extra comments to let you more easily see what the correspondence is between lines of assembly code and lines of the original source code. So for example, it might have like lines of individual source code included as comments in the assembly code. So you can look through the assembly code and go, oh, these assembly instructions here match up with this particular line of source code and so on. So often you'll use these two options together just to make the assembly code a little bit more easy to digest. And Clang also has loop vectorizer and basically basic block vectorization as well. Clang supports also most features of OpenMP 4.5. So both of them are, both GCC and Clang are pretty good for supporting OpenMP. In the case of Clang, it's a little bit more, I guess, aggressive in terms of doing vectorization in the sense that you only have to enable optimization level of 1 in order to turn on vectorization, whereas with GCC, it's a level of 3. And then there's a number of options again for Clang, and unfortunately there are some command line options that are different between GCC and Clang. Clang basically has a shorter history. It came along after GCC, so to try to make things sort of more compatible between the two compilers, a lot of the options are the same. But once you start to get into some of these kind of more advanced things, like trying to fine-tune optimization and stuff like vectorization, they start to kind of diverge more. But you have options that kind of achieve similar goals. So the ones that I've highlighted in the kind of the magenta colored font or whatever, this is kind of illustrating the ones or emphasizing the ones that are maybe more likely to be more helpful to you, like in terms of which ones are maybe relatively speaking more helpful than others. So in the case of Clang, if you want to enable the vectorization, you use the -F vectorize option. So I guess even if you have like optimization level of 0, if you want to turn vectorization on, I guess you can use this option here. And it has options just like with GCC where you can say, please like output informational messages when I'm compiling to tell me what loops actually were vectorized and also like which ones couldn't be vectorized, which is often a very helpful thing to know. As I mentioned before, there's a -S option, which is similar to both GCC and Clang, which allows you to get the actual assembly language that was output instead of object code. So that's basically the kind of the key options with respect to Clang. In terms of trying to assess the quality of vectorized code, like as I mentioned, often you'll want to look at assembly code that's generated by the compiler, because even if the compiler is able to generate informational messages and tell you that, yes, I did vectorize this loop or I did vectorize this piece of code, you might still want to know what was the actual assembly code that was generated, because sometimes the compiler does a much better job than others. And if it's really a key part of your code, like it's really a performance bottleneck that you're trying to focus on optimizing, you might care very much about the particular sequence of CPU instructions that are generated. So on this slide here, I have a very simple like inner product calculation, basically just computing the dot product of two vectors. So you have like a vector of floats, another vector of floats, and then like the size of the vectors, basically n here. And it's just doing a single loop, a sequential loop, just computing the dot product, and then it returns the dot product result. And suppose for some reason you want to know like what code was actually generated for this loop here, and maybe this is embedded into a much larger source code file. So maybe there's thousands and thousands of lines, and you just want a little bit of help to try to pinpoint the particular place that corresponds to this loop. You can do things like there's this ASM volatile kind of directive. I don't believe it's formally part of the language, but a lot of compilers support this kind of thing where you can essentially embed directly assembly code into your source code. So like at the point in the assembly code that corresponds to this point here, it will actually inject this assembly code into it. And a number sign is just starting a comment. So what I'm doing is I'm injecting a comment into the assembly code that gets injected just before the code for the loop gets generated, which is saying the loop is starting. And then just after the loop, I'm injecting a comment in the assembly code saying loop end. And then on the next slide, I have an example of the output of like a portion of the assembly file that I end up with. So this is for x86, like compiling for x86 architecture. So I think this has been abridged somewhat because there's assembly files are quite verbose. There's a lot of junk in them. But the key thing to notice here is, here's the comment that I kind of injected with that ASM directive, loop start, and then down at the bottom, toward the bottom here, we have loop end. So essentially the stuff between these 2 points here is the stuff that's corresponding to the loop. And we can kind of see what's well, if you're familiar with, I mean, I'm not an expert in x86 assembly, but at least I can kind of look at this and get the general gist of what's going on. It looks like it's setting a counter here. It's setting a register here to 0. If you XOR, exclusive OR something with itself, it sets it to 0. And then it's doing some kind of vector operation here. This is the top of the loop. This is a label in the assembly code. So here, this is basically testing the condition at the top of the for loop. We're using a for loop, and there's a condition that's tested at the top. If the condition that's true, it jumps over the body of the loop and at the point after the loop, which is down here. Otherwise, it goes into the body of the loop. And the key thing we'd probably be interested in here is what instructions are being used here. And these ones that start with V, I believe, are vector operations. It's using like the XMM registers, which are, I believe, vector registers on x86. So we're doing like some vector operations here. This is incrementing our counter for our loop, and then it jumps up to the condition that we check at the top of the loop. And eventually, we'll take this branch, which basically ends the loop, and we jump down past the code that's at the end of the loop. And at the end down here, we just return. Anyway, it's not so essential if you understand assembly language, but at least this is the kind of ideas that you might want to look at the assembly code and maybe be focusing specifically on like what's happening inside the loop, because that's probably the thing that's most critical to the performance of the code. Any questions? Maybe one other thing I can point out as well is that you can see here that there's something called name mangling. Like for example, in C++, because you have like overloading of functions, you can have many different functions with the same name. Linkers are stupid. They can't really, or at least generally they tend to be stupid. They can't handle different things, like different things having the same name. Everything has to be uniquely named. So because of this, at least on any platform I've seen, that when you go from the compiler to the linker, there's a transformation called name mangling that's applied to all the identifiers in the program. So this function that's called _z9 inner prod pfs _I, this is our inner product function from the previous slide. And basically embedded into this name is the types of the arguments for the function. Like I think if you go back to the previous slide here, we're taking like a pointer to a float, and then an integer n. And essentially embedded into this, I can't remember offhand the rules for mangling and so on, but basically embedded into this is the types of the arguments that are being passed to the function. Because different overloads of the function will have different arguments, different types, and different numbers of parameters, they will have different names after you mangle them. Anyway, but this makes things a little bit more painful when you're looking at assembly code too, because the names are all mangled. There's some filters that you can run programs through that unmangle things, but anyway, enough about this example. So auto-vectorization with hints, again, as I was mentioning before, essentially all this does is we now are going to add annotations to our code to try to give hints to the compiler about when optimization might be legal to do. In other words, it's not going to change the behavior of the program. It's a safe transformation to apply, or to give hints that would indicate to the compiler, well, yeah, this is probably a profitable thing to do. It's actually worthwhile to do vectorization. And this is really, I guess, the main thing we're going to focus on in the course is adding hints. And there's various different types of ways that we can annotate our code to indicate to the compiler some of the things that might be preventing the compiler from being able to do vectorization. We can give hints that would indicate these things aren't going to happen. In other words, the compiler doesn't need to worry about it. So this sort of approach is relatively easy to use because it's not too difficult in terms of the types of ways we annotate our code. It's kind of fairly simple to add these annotations. The downside is, though, that we're essentially saying to the compiler, like, trust us. We know the code really well, better than you do. We know that in this particular case, for example, maybe these 2 pointers can't alias. So you don't have to worry about when you're optimizing that if the 2 pointers alias to the same chunk of memory, that this could cause the way that you optimize the code not to work. So if we do these things, if we annotate our code in this way and we're wrong, we say, compiler, trust us, you don't need to worry about this issue, and we're wrong, then the compiler will probably generate code that's not valid. And then who knows what our code is going to do when we run it. It definitely is not going to do the right thing. We can get maybe various kind of strange failure modes. So that we have to be very careful when we start adding annotations to our code that the promises that we're making to the compiler actually are true. But at least this is not as bad as maybe having to write our own assembly code from scratch, for example. So what are some of the obstacles to vectorization? I think I touched on a few of these before, but essentially there's quite a few things that can stop vectorization from happening. One of them is data dependencies, because, for example, if you're vectorizing a loop, effectively what you're doing is you're changing the order in which the computations that are done in that loop, you're changing the order in which they're being done. If you take a sequential loop and you vectorize it, what you're doing is you're taking things from the sequential loop that always happen one after the other. Each iteration happens before the other ones. But if we vectorize a loop, then what we're doing is we're taking a bunch of iterations, having them all run in parallel. So we're changing the time at which things are happening. Because of this, if there's dependencies on different iterations, in other words, some data from one iteration is feeding into another iteration, like it's being written in one iteration that's earlier and then being read in a later iteration to be used. If we then change the order things happen in, the value we read might not be the right one. So data dependencies can cause problems with respect to vectorization. Another thing that can cause problems with respect to vectorization are control flow dependencies. So this is basically branching, things that branch. So for example, suppose that you have a loop, and inside the loop there's something that's kind of very nicely vectorizable, but then you have an if in the loop, where sometimes you do one thing, other times you do something else. This becomes difficult for a lot of architectures to be able to handle in terms of vectorization. Because when you're doing vector operations, there's not an easy way to say, well, like add some of these elements of this vector to this one, but for this one element, I don't want to add, I want to multiply or something like that. Like you have to do the same things to all the elements in the vector. So once you start having ifs, effectively what you're doing is you're saying, well, sometimes I do this, sometimes I do this other thing. And then it's hard to vectorize because the vector operations want to do the same thing to everything that's in the vector. So sometimes control flow dependencies, at least if there's enough of them, and there typically probably doesn't need to be that many before the compiler just gives up and says, I'm not even going to try to vectorize this because it's just going to make the code maybe even slower than it was before. Another problem, which I kind of mentioned a few times, is aliasing. Aliasing can be a huge problem because essentially what aliasing can do is it can introduce data dependencies that aren't immediately obvious in the code. Because essentially what it means, if you have two pointers aliasing, like two pointers that are pointing into the same region of memory, what this means is two variables that you would think that if you modify one, it can't affect the other one. Suddenly now modifying one can affect the other one because they're referring to the same area of memory. And this introduces dependencies between the data, and these dependencies could cause things to break if you start vectorizing code. Another thing that can cause problems is non-contiguous memory accesses. So like when you're accessing, for example, if you have a vector load, like you're loading a vector register from memory, typically the elements of the vector you're reading have to be contiguous in memory. You can't kind of do like a gather read, for lack of a better thing to call it. Like you can't kind of grab a bunch of values that are scattered all over memory and bring them into a vector register in one operation. So for this reason, if you have a memory like values that are not contiguous in memory and you want to do vector operations on them, it's very difficult to do this in any kind of efficient way. Another thing that causes problems as well is misaligned data. So it may be the case that for the vector operations you're trying to perform, there might be some kind of stricter alignment requirement that's required for like basically loading and storing vector registers. And maybe the data is aligned not aligned appropriately, so it can't actually use a vector operation to read things because the instruction can't actually handle that misaligned data. So there's like basically a lot of things that can kind of go wrong and prevent vectorization from being able to be applied. And some of these things are things that maybe they're not an issue. We know that they're not an issue in the code. Like maybe we know because of a way of functions being called that aliasing can never happen. But when the compiler is looking at it, it just sees two pointers, maybe as parameters to the function. It has no way to know when you call those functions, aliasing can't happen. So these are the sort of circumstances where sometimes you'll be looking at your code saying, why did the compiler not vectorize this? But it's these sorts of issues, like maybe because of the way their code is actually being executed. You have some function where there's two pointers being passed in. They could theoretically alias, but maybe you know that you never call them in a way that they would alias. But when the compiler is compiling that function, it doesn't know that you're always going to call it in a way where aliasing doesn't happen. So these are the sorts of things that can cause vectorization to not be performed. So if we look at each of these different issues in a little bit more detail. So the first one, I'm just, I think, going to follow the order that was in the list on the previous slide. So the first thing to look at is data dependencies. So again, data dependencies, when we're doing vectorization, essentially vectorization changes the order that computation takes place in. Things that were previously happening in the sequential ordering become happening in parallel. And when this is done, because we're changing the order, depending on how the different computations feed into one another, how they relate in terms of data dependencies, we may break the code and have it actually do a different computation from before. So there are three types of data dependencies. What's known as a flow dependency, sometimes called a read after write dependency, an output dependency, which is sometimes called a write after write dependency, and an anti-dependency, which is sometimes called a write after read dependency. And of these three types of dependencies, the ones that are most problematic with respect to vectorization are the first two. In other words, flow dependencies and output dependencies. So again, looking at these different types of dependencies in more detail, the first is what we call a flow dependency, which is sometimes called a read after write dependency. And basically what this is where you have like a loop and you're reading a value in a later iteration that was written in an earlier iteration. And this can potentially cause problems if you start reordering how things are computed by doing vectorization. And related to this is what's called the dependency distance. And this is probably best explained in terms of an example. But what this is saying is like, what's the difference in the iteration number between the thing that's reading and the thing that's writing if you have one of these read after write dependencies. So in this code example here, we have a loop. We're looping from I equal 1 up to, but not including n. And we're performing this computation in the body of the loop. So what you can see here is in the iteration I, what we're going to be doing is we're going to be reading a value that was written in an earlier iteration of the loop. In an earlier iteration, this value is written because the thing that's being written is index I. So here we're going to be reading something that was written in an earlier version of the loop. But in particular, the thing that we're reading here was written in an iteration that differs by 1. Like the thing we're reading here was the thing that was written in just the immediately previous iteration. So the dependency distance, which is the difference between the two iterations, like the one where you're reading and the one where you're writing, is 1 in this case. So the dependency distance for this code example is 1. And basically, the smaller the dependency distance is, the more problematic things are when you start to vectorize the code. In more specific terms, if the dependency distance is less than the vectorization factor, then the vectorized loop can't be guaranteed to yield the same result as the unvectorized version of the loop. And basically, the reason for this is the following. With the flow dependency in our original unvectorized loop, essentially what we have is a value that's being written in one iteration and then read n iterations later, where n is the dependency distance. What's critical here is that the read occurs after the write. If, however, we vectorize the loop with a vectorization factor that exceeds the dependency distance, then the read of the value associated with the flow dependency will happen in the same iteration of the vectorized loop as the write of that value. In other words, the read happens at the same time as the write, not after it. Consequently, the value read in the vectorized loop will not be the same as in the case of the original unvectorized loop. Thus, the original and vectorized loops will not be equivalent in terms of the computation that they perform. And I have a code example to help sort of illustrate this. So what we have is this particular loop here that we want to contemplate vectorizing. And we want to vectorize it with a vectorization factor of 4. So we're going to group together like 4 operations at a time. We're essentially like doing an add operation inside this loop. So we're going to effectively convert this into a vector operation that adds 4 values at once, and like also probably does a vector assignment as well. If we look at this loop in more detail, essentially this is going to exhibit a flow dependence with a dependence distance of 1. In other words, we have one of these read after write dependencies where we're going to be reading, for example, this element here in the iteration immediately following the one where we wrote it by this is left-hand side of the assignment here. So this exhibits a dependence, flow dependence with a dependence distance of 1. If we now say, well, let's actually try to vectorize it with a vectorization factor of 4, how would we do this? Well, essentially, we want to unroll the loop 4 times, because we want to unroll it sort of the number of times that corresponds to the vectorization factor. So if we unroll it 4 times, we transform the loop from the above loop here to this new loop here. And I'm going to assume that the number of iterations is a multiple of 4. If it's not, then we would need to do some extra stuff to handle sort of the startup condition for the loop and the ending condition for the loop separately. But just to make the example simpler, I'm going to assume that n is a multiple of 4, so that this groups into like an even number of iterations, like an integer number of iterations for the vectorized loop. And the basic idea here is we're going to use vector operation for the addition. So essentially all these elements of a minus 1, I plus 0, I plus 1, I plus 2, these 4 elements here would all get read into one vector register. These elements in B, here, B, I plus 0, I plus 1, I plus 2, I plus 3, they also all get read into a single vector register. Then we do a vector add to add them together, and we write the result using another vector operation, like a vector store, to write into these array elements here. So the vectorized loop using this kind of non-standard, like non-C++ syntax looks something like what's shown here. It turns out, though, that if we actually vectorize this loop, like if we replace this loop here with this new code here, we're going to end up computing a different result. or at least there exists some input data that we could have that we would compute different results. The code is not equivalent. And basically the problem here is the dependence distance, this value here of 1, it's less than the vectorization factor. And essentially what this is saying is that the dependence distance is saying like how close together loop iterations are using data from each other. So the smaller this gets, the more things depend on closer together iterations of the loop. So if we take and vectorize with a factor of 4, we're taking sort of a group of 4 consecutive iterations and compressing them into 1. But because the dependence distance is so small, what's going to happen is there's going to be some values that we'll use in the vectorized loop. We're using them at a point where they're not having the right value initialized yet because we're using them sort of too early. And I have a code example to sort of illustrate this. So if we take the code that we had previously, this sequential loop here, suppose that we initialize some of our data that we're operating on in this particular way. So we essentially have a loop, or sorry, we have an array A and B, which are pointed to by these pointers here, where each have 5 elements, which are initialized to just some simple values, simple integer values, -1 through -5 and 0 through 4. And then what we're going to do is we're going to execute this loop here, which is just computing a sum and storing the results into A. So if we kind of walk through the loop and see what it's doing, in the very first iteration, we're starting from 1, not from 0. So when we're iterating the very first time, we're going to be setting A1 from A0 by adding to it B1. So essentially what we're going to be adding is, I guess, A0 plus B1. So -1 plus 1. These are the values that we'll be reading out of these 2 elements to add, which gives us 0 when we add them. So the first element that would be written into A of 0 here in the first iteration of the loop would be 0. And we can walk through the rest of the loop as well if we want. And the values that we'll end up computing is 2, 5, and 9. So when all is said and done, this vector, or this array A is going to have the values 0, 2, 5, 9 written in the later elements, the ones that we're updating. If we then take this loop and we vectorize it, so this is what's shown on the next slide. So we have like identical code, identical data that we're feeding into the code, but we're going to vectorize it with a vectorization factor of 4. So we're going to take 4 iterations of the loop and group them together into a single iteration. And because in this case there were only 4 iterations of the loop, when we group them into a single iteration, we're actually only going to do 1 iteration of this vectorized loop. So effectively the loop kind of goes away. It's just all done in 1 vector operation. But if we walk through and do the calculation again using the vectorized version of the loop, again, we're doing exactly the same computation as before, except it's been vectorized. But the vectorization is going to break things. We're going to end up with a different result. And this is kind of easier to compute because we are doing it all in one step. So essentially what we're doing is we're loading the values of A indexed from, well, initially I is 1. So it's going to be from A of 0 up to, I guess, A of 3. So we're going to be reading like these values here, -1, -2, -3, -4. This is what's loaded into the vector register that's going to be holding the values from A. And then for B, we're going to be loading the values, again, I is equal to 1 in the iteration, only iteration of this loop. So we're going to be loading B1 up to B4. So B1 up to B4 are the values 1, 2, 3, 4. So we're going to load these values. And then we're doing a vector addition. And I've just chosen the numbers to work out very nicely. So everything cancels. You get -1 plus 1, which is 0. So the first element is 0. Then -2 plus 2, which is 0. And effectively, all the terms are going to cancel. And we end up with all zeros being calculated. So when this code actually finishes, we end up with all zeros for the elements that are actually computed. But if you compare this to the previous slide, like it's exactly the same code with exactly the same data, but it's computed completely different values. In other words, we've broken the code by vectorizing it. We've changed the calculation that's actually being performed. And again, the issue here is that the dependence distance is too small for the amount of vectorization that we're performing. The vectorization factor is 4, and the dependency distance, I believe, is 1 in this case. So this kind of breaks things. So this is the kind of analysis the compiler tries to do when it's trying to decide whether or not it should even contemplate vectorizing the code. The first thing it's going to do is figure out what are the different data dependencies, for example, for a loop, figure out what the dependence distance is, and then figure out what vectorization factors are available to us for a particular architecture. There may be different choices that can be made in terms of what the different vector lengths are, maybe like 2, 4, and 8, maybe it can choose from or something like that. And it can figure out, well, are any of them going to be safe to perform? After it determines that, then it may also ask the question, like, is it likely to be profitable to do this? Because you don't want to optimize things if it's not going to help. But in this case, the compiler would just stop at the point where it goes, this is not safe. I'm not going to apply this transformation because it will change what your code's actually computing. Any questions about the example? Then just another example, which is slightly changed in a way where the dependence distance is larger. So essentially, there's the place where you're kind of you're like reading a value maybe that was written in an earlier iteration of the loop. Now these iterations are further apart. They differ by a larger number of iterations. In this particular case, the code that we have here has a flow dependence where the dependence distance is 5, because what's happening is when we're reading this value here, a of I minus 5, the value is written 5 iterations earlier, like because the difference between this index here and this index here is 5. So it was essentially 5 iterations earlier where that value was being written. And if we vectorize with a vectorization factor of 4, because this value of 4 is less than 5, what this means is that any of the dependencies between the data will still be between different iterations of the vectorized loop. So there won't be dependencies within a single like block of the vectorized loop, because if there were any, because we're doing this part of the calculation in different order, we can end up with a different result. This is maybe the best way that I can explain it. So if we apply a vectorization factor of 4 for this vectorization, what we'll do is we'll unroll this loop 4 times, which is what's shown down below here. Again, in this example, I'm going to assume that the number of iterations, n, is a multiple of 4. Otherwise, this is not going to quite work because it will either do too many or too few computations. But we'll just assume that the number of iterations is a multiple of 4. Then when we convert this into a vectorized form, just writing in a sort of non-standard syntax, we have something that looks like this, where we're going to be basically reading 4 elements out of A, reading 4 elements out of B, and then adding them together, and then writing those 4 elements into to A here. But when we do this, though, this is guaranteed not to have any problems in the sense it will always compute the same thing that the unvectorized sequential loop would compute. And the way we can be confident about this is because of the fact that the vectorization factor 4 is less than the dependence distance. So although we're reordering things by vectorizing, we're not reordering things so far that something is trying to be used before it's actually been initialized the way that we want it from an earlier iteration of the sequential loop. Any questions? Another type of dependency that we can have is what's called an output dependency. And I think it's more insightful, the other name that it's referred to as, which is a write after write dependency. It kind of gives more hint in terms of what it really says. And basically what it's saying is you have, for example, you have a loop where something's being written multiple times as you're looping. So you have a write to a variable, and then you have a write in a later iteration. So this would be an example of code that exhibits an output dependency. Because I'm doing I modulo 2, what this means is like one iteration I write to A0, the next iteration A1, A0, A1, A0, A1 as I'm iterating. So I'm going to be writing to the same location in multiple iterations. And generally, when you have output dependencies, this tends to be problematic with respect to vectorization of loops. So you want to try to avoid doing vectorization in this sort of circumstance. And I think I'll stop here for today because I'm just about to run out of time.